Okay, so hello everyone, welcome to our numerical analysis seminar. This is our third talk this semester, and I'm going to give a brief introduction of our speaker today. So Dr. Longfei Li received his PhD from University of Delaware in 2014, after which he worked at RPI as a Margaret Darwin postdoc fellow. He is now an assistant professor of mathematics at University of Louisiana at Lafayette. His research focuses on high-performance scientific computation and numerical analysis, as well as mathematical modeling and high-fidelity simulations. Today, he'll be talking about numerical methods for fourth-order PDEs on overlapping grids with some applications to Kirchhoff-Love plates. Thank you, Longfei. The floor is yours.
Okay, thank you, Hanji, for the nice introduction, and thank you for inviting me, and thank everybody for coming. Okay, so this is your third talk. So this is actually my first talk since pandemic. So hopefully I still remember how to talk. Okay, so yeah, so this is a joint work with Hanji Ji and Chi Tang from Nano. Okay, so I will be talking about our new numerical methods for solving a type of fourth order PDEs on overlapping grids. And we will show you some application of our new methods for solving Kirchhoff plate problems. Okay, so the outline of this talk is first, I'm going to give you some introduction about the background of the problems, like what has been done and where the difficulty is. And I will talk about the specific governing equations we're looking at to solve. And I will go a little bit detail about the numerical methods. So we're going to use a type of method called a composite overlapping grids for solving PDEs on complex geometries. So I will spend some time talking about what is a composite overlapping grids. And then I will briefly describe about our spatial discretization technique on curvilinear grids, and then the time stepping scheme for integrating those equations. So we've conducted some stability analysis that help us to determine like the stable time step for our schemes that can be used in real computation. And then using a model problem in 1D, I illustrate all the numerical difficulties we're facing and how our proposed approaches will address those issues. Okay. And then I will show you some numerical results. To wrap up our talk, I will give you some conclusion and talk about some future directions where we can bring this research to some other applications. Okay, so time-dependent PDEs involving fourth order spatial derivatives arise in many mathematical models. For example, in the parabolic form, we have the well-known Kirchhoff-Love equation, right? So we have a fourth order derivative here. And also we have the thin film equations, right? So we have a fourth order derivatives here. Okay, so it's called a parabolic because it's the time derivative in this type of PDE is only a first order. Okay, and also they appear in hyperbolic form, so which means we have second order time derivatives. So this type of equation appear in beam or plate models, so something like that. So this is a very simple plate model that governs the bending of a plate. Okay, so it is numerically challenging to solve this type of fourth order PDEs, and especially if we want to solve them with complex geometries. Okay, so this work focuses on solving a class of fourth order hyperbolic PDEs. So basically it means we have second order time derivatives and up to fourth order spatial derivatives. And we're going to solve this type of equations on general geometries. Okay, so we all know that high order derivative plus general geometries means a lot of numerical challenges. Okay, so there's a lot of existing work has been devoted for solving this type of equations. Okay, so broadly speaking, we can have a lot of finite element based methods. So for finite element based methods, we can use a mixed finite elements. So basically we reduce the order of spatial derivative by introduce some auxiliary variable, right? So for example, if you have biharmonic operator, you can model it as a system of Laplacian equation, right? But the good thing is that we reduced the order of derivatives, but the bad thing is because the auxiliary variable, it's kind of hard for us to find a boundary condition for that, right? So it will not work for all the boundary conditions. And also there's a method for trying to solve this high order derivatives directly using C1 conforming finite elements. And of course, if you want to use C1 conforming finite elements, that's very complicated. And it gets even more complicated if you're trying to do it with higher dimensions. Therefore, I think right now there's maybe only beam models, they use C1 finite elements, but for plate models, for 2D or 3D models, we haven't seen anything doing that. Okay, and there's other methods using non-conforming finite elements, for example, the Will-Morley elements, or this discontinuous DG method, as well as isogeometric analysis and its variants, which has been emerging recently for solving this type of high order PDEs. And on the other hand, we have finite difference method. So for the finite difference method, we're kind of behind, right? So similarly as the mixed finite elements, we can also reformulate the PDE as a system of lower order PDEs, right? So like a system of Laplacian equations. And the same thing, the drawback of this type of method is it's kind of hard to find a physical boundary condition for the new variable that was introduced artificially. Okay, and of course, there's also direct finite difference approximations for those high order derivatives, but mostly this kind of direct finite difference approximations happen in rectangular or simple domains. Okay, so in this project, we're going to bring the finite difference method for solving this type of problems for general geometries, and we're going to use a technique called a composite overlapping grids to resolve the geometry. Okay, so to be specific, the governing equation we consider for this project is a type of linear fourth order hyperbolic PDE. So we have second order in time and up to fourth order derivatives in space. So for simplicity, we only consider linear type of problems, right? So all the operators are linear here. And the boundary conditions are normally we have, for this type of boundary conditions, we normally have the Dirichlet boundary condition of the first type. So basically we specify prescribe the W value and also the normal derivative. And also we have the second type of Dirichlet boundary condition. So we specify W value and specify some maybe a Laplacian of W or some combination of second order normal and the tangential derivatives, right? So this type of boundary condition is also referred to as Lafayette boundary conditions by some other authors. Okay, so we have, of course, we have the Neumann boundary condition, which concerns the second derivative and the third derivatives of the unknown. And okay, so to complete the statement of this problem, we need to specify initial conditions. So basically, we just specify the initial W and the initial time derivative of W, right? So here, the F and all the parameters are assumed to be constant. And here, dn and the dt are the normal and the tangential derivatives. Okay, so here w0 and the y0 are the given functions for our initial conditions. Okay, so in the context of plate theory, so this model basically describes a generalized Kirchhoff-Love plate model. And the physical meaning of W is the transverse displacement of the reference surface of the plate. Okay, so and in this context, those three boundary conditions has been referred to as clamped boundary condition, or the supported boundary condition, or the last one is called a free boundary condition for plates. Okay, so in this work, our method will be applicable for all those boundary conditions without any problem. Okay, so like I said, our goal is to resolve two challenges. First, resolve the high order derivatives. Second, we want to do it on general geometries. So we're going to use a technique, it's called a composite overlapping grids. Okay, so composite overlapping grids are efficient and powerful techniques that is often used for solving PDEs in domains with complicated geometry. So here, this is an example of a composite overlapping grids we have here to discretize this region that is a square with a hole cut in the center. Okay, so generally speaking, a composite overlapping grid, here we call it G, is basically a connection of component grids. So in this particular case, we have two component grids. One is a green grid, the other one is a blue grid. Okay, so the component grids, they are structured component grids, and their union will cover the entire domain, and they will overlap where they meet. Okay, and each of this component grid is logically rectangular. What does that mean? It means we're going to be able to map it from a unit square. So in a reference domain, we have a unit square, and we map the physics space to that. Okay, and the solutions that is on different component grids are coupled together by interpolation. So you can see from this example grids here, we have highlighted the interpolation points here. So the solutions on those grids will be coupled together by interpolation with contributions from the neighbors from the other grids. Okay, so the good thing about this type of method is we are able to resolve complicated geometries just by putting more component grids to resolve whatever geometry you want to resolve. And another good thing about that is each component grid is logically rectangular. So in other words, they are structured grids. So by working with the structured grids, we have nice features, nice structures of the matrix as a result of the discretization. So that normally means we will have, we can design very efficient numerical methods for dealing with or manipulating all those matrices. Okay. Okay, so here, so how do we discretize derivatives on a component grids? So first of all, we're going to transform it to a reference space and then approximate using on the unit square using standard finite difference formulas. For example, for the biharmonic operator, after transformation to the reference domain, we have very lengthy expressions. Yeah, the transformation, of course, is done automatically by some symbolic toolbox. Okay, so not by hand. So we fortunately we can do this type of transformation very conveniently, and we can write code to export actually the C++ code we used. So everything has been automated, so we don't have to worry about the lengthy calculations by hand. Okay, so after the transformation, we can see that we will be able to approximate the red derivatives here. So the red derivatives are all the derivatives in the reference domain, RS domain, right? So because the RS domain is the unit square, so we can use the standard central finite differences. And the other things, they are just given by the mapping, right? So we are given this mapping that maps from the unit square from the reference space to the physical space. So we will have values for those things here. With that, we will be able to approximate a biharmonic operator on curvilinear grids. Okay, so after discretization, our equations can be conveniently or concisely written into a matrix into this following form, right? So M is my coefficient, and the second derivative in time, and this LH is like simplification for all our spatial derivatives, right? Discretize the spatial derivatives, apply that to this ij point and the Fij here. And for numerical purposes, we propose to add artificial hyper-dissipation into this system. So the hyper-dissipation takes this form. So this new AD is a parameter we can use to control the strength of this dissipation to add. And this DAD, the dissipation operator, is given by a fourth order hyper-dissipation. So we only dissipate into the R and the S directions, and we don't worry about the mixed directions. And this turns out to be fine. Okay, so why we want to add this kind of artificial dissipation is because when we use our numerical method for solving problems on overlapping grids, we observe that there is some weak instability that is caused by the presence of interpolation equations, right? So we said that in addition to this finite difference approximation, as we see here, we also add interpolation equations that will couple together solutions on different component grids, right? So the presence of those interpolation grids will damage or the nice structure of this finite difference operator, right? So for finite difference operator, everything is symmetric. But if we have to add some interpolation, so the whole system is no longer symmetric, right? So it damages the symmetry of the matrix. And because we only have a few interpolation points, so So like the damage is not very strong. It basically just introduced a little bit of perturbation into our matrix. And because we're solving hyperbolic equation, right, we tend to use non-dissipative schemes because we want to preserve some nice structures and we want to see some non-time behavior, right? So if we use dissipative schemes, it will damp out those nice features. So we normally don't want that. So which makes this type of method very sensitive to any perturbations. And we will see that by adding this artificial hyper-dissipation, we will be able to stabilize those instabilities introduced by interpolation, and everything works nicely. And we will show this in a simpler 1D model problem, so to make it clear. Okay, so but before we do that, let's finish the statement about the algorithms we proposed for solving this type of equations, right? So we have actually proposed of developed 4 time stepping schemes for solving this for integrating this equation in time. Okay, so the first is referred to as a C2 time stepping scheme. So given our solution at the previous 2 time levels, our output will give us solution and the time derivative and the second time derivative of the solution here. Okay, so our algorithm will produce, so thinking about a plate, so our algorithm will simultaneously produce solutions for the displacement, velocity, and acceleration. So why we want, unlike many existing methods who only compute the displacement, why our method want to compute the velocity and acceleration is that our goal of solving this type of equation is not just solving this type of equations. We want to couple it with fluid solvers so that we can do fluid structure interaction type of problems. Therefore, when you're coupling 2 systems together, we need the information about the velocity and acceleration of the structure. So therefore, it is essential for our future work to have an accurate velocity and acceleration solution as well. Okay, so the C2 scheme is very straightforward. We simply advance the time derivative using centered time difference scheme. So we have a centered time difference scheme, and we treat the dissipation term using a backward differentiation, right? So backward difference in time. And this way we incorporated this artificial dissipation explicitly. As a result, the whole scheme is still explicit. Okay. And another thing is called a UPC2 scheme. So we notice that if we incorporate the artificial dissipation explicitly, like what we did for the C2 scheme, we have a reduced time step restriction, so which is not, that is something we don't want. Therefore, we would like to incorporate it implicitly, but we still like the efficiency of an explicit scheme. So therefore, we designed an operator splitting strategy to incorporate this artificial dissipation explicitly. Okay, so the algorithm goes like that. So we predicted the solution without artificial dissipation using the C2 scheme, as we've seen it before, right? So the second order time derivative to approximate that here. And then we correct the solution with the artificial dissipation using the predicted value of my displacement. So this way, from our analysis, we can see that the resulting time step restriction is not reduced because of the introduction of this additional artificial dissipation. Okay, so the remarks is that the only difference between the C2 scheme and the UPC2 scheme lies in the treatment of this artificial dissipation term, right? So for the C2 scheme, we treat it explicitly using a backward time difference formula, while for the UPC2 scheme, we treat it using an operator split strategy, so that both schemes will remain explicit with or without artificial dissipation. We may also solve this type of equation in a first order form. So, right, we may convert the second order ODE into a system of first order ODE, right? So by introducing V and acceleration. So we have this artificial dissipation here. And we may have tried some method before, right? So Hangji and I had some previous publications using this method for solving plate equations, but those things has been limited to a simple geometry with like a rectangular geometry, right? Without we don't have to use any overlapping grids. And this method works fine for a single grid case. But when we try to apply this method directly for overlapping grids, we quickly observed that it is not going to work. We have to add this artificial dissipation to stabilize things. Therefore, as a comparison purposes, we also it's like fix our previous algorithms, making it work for the overlapping grid case. Okay, so the idea of this predictor corrector PCA22 scheme is that we use an Adam Bashford second order predictor to predict all my WV and acceleration, right? So this is standard Adam Bashford second order predictor. And then we corrected it with a modified second order Adams-Moulton scheme. So we know that Adams-Moulton is implicit scheme, but we modify that instead of evaluating the thing at n+1, we use a predicted value from the predictor stage. Therefore, the resulting scheme is still remain explicit. Okay, and also for solving beam type or plate type of equations, engineers have been using this famous Newmark beta scheme. Okay, so and again, we were trying to apply this Newmark beta scheme directly for solving our equations on overlapping grids. It's not working. So even though this is implicit scheme, it should be stable unconditionally, but it's not working. So from our 1D model problem, you will see why it's not working. But here, we just say that we implement a second order type of Newmark beta scheme with this specified parameters in a predictor corrector fashion. So we first predict a first order prediction for my displacement and the velocity. And then we incorporate the artificial dissipation implicitly. So it appears on both sides of this acceleration equation. Once we solve the acceleration equation at the new time level, we're going to correct it with the new acceleration for our displacement and velocity. Okay, so from these schemes, we would want to know two questions. How can we determine the strength of a dissipation to add? How much dissipation is enough, right? So we don't want to add too much dissipation so that it will damp out all those important features we're interested in. And we don't want the dissipation to be too little so that it's not going to suppress the weaker instability introduced by the interpolation. So we want to address this type of question. And also for any time stepping schemes, we want to know how to determine a stable time step so that it will work naturally in any computation. And we use a yo-yo technique of local Fourier analysis with freezing coefficients. So basically we freeze all the coefficients and we do the discrete Fourier transformation of our discretized equation. So we end up with in the Fourier space, we have the transformed equation. And any particular time stepping scheme is going to be stable if it is stable for this transformed equation for any wave number. Therefore, based on that, we can derive a sufficient condition for the stability of the scheme by considering the worst case scenario of all the modes, right? So the worst case modes corresponding to the psi values to be plus pi or minus pi. So this corresponding to the plus minus modes in each direction in the reference domain, right? So you just imagine your wave is like a +1 or -1 wave. So those are the worst case scenario. So if our scheme is stable for this worst case scenario, the time step restriction we obtained from this analysis shall be enough for our real simulations. Okay, so we just did that analysis for all our, so we used all our 4 numerical schemes to solve this transformed equation, and we derived those time stepping restrictions. And so it looks very complicated, but it's here just like to point out that the time step is depending on the worst case scenario, right? So this is the Fourier transformation of the worst case. And we can see that from the comparing the UPC2 scheme and the C2 scheme, there's no time step reduction comparing with or without artificial dissipation, because the way we treat how we added artificial dissipation into the scheme. And also to compare with our previous study on a single mesh, we also derived this time stepping scheme for the PC22 and MB2 schemes, right? So For the NB2 scheme, because it's an implicit scheme, so we just use the same time stepping scheme, but with a much larger coefficient to multiply that, because it's implicit, it should be unconditionally stable. But for accuracy reasons, right, because we want to, we use the second order finite difference for spatial discretization, so we don't want to take too much time step, so that we are not going to resolve the second order accuracy in space. Therefore, we have to use, we cannot take too much time step. And also we have derived the formulas for adding how to determine the strength of artificial dissipation, so that it will stabilize our integration. Okay, so now we've seen, I've been talking about that we have trouble working with overlapping grids about some kind of weak instability. But why we have that kind of weak instability? So here we're using this model problem in 1D as an illustration to show you why we have this type of weak instability. And also using this model, simple model problem, we're going to show you how the artificial dissipation we added to the scheme help to stabilize our simulation. Okay, so the simplest fourth order hyperbolic equation we can think of is, of course, this one, second order in time and the fourth order in space, and on a domain from 0 to 1. Okay, so for simplicity, we just consider the clamped boundary condition. So we specify W equals 0 and the second derivative equals 0 on the ends. Okay, so we are going to discretize this model problem on both a single grid. So you can see the black grid here on a single grid, as well as on a composite overlapping grid, which consisting of two component grids shown here, right? So we have one component grid going here, another component grid goes that way. Okay, so on a single grid, of course, we can discretize our fourth order derivatives using standard finite difference formula. So this is a finite difference operator. For that, this tells you we have to do the fourth order derivative in W direction. And this is how we approximate to the fourth order artificial hyper-dissipation. Okay, and on the boundary, we use standard finite difference. Okay, so we also, as you can see, because we want to keep everything centered, we have to add two ghost points on each side. So we have ghost points. And to determine the second ghost point, we can simply use extrapolation. Okay, so on the composite grid here, for each of the interior of this interior points, we can use the same thing, right? The standard finite difference approximation. And on one of these ends, we can have the standard approximation of the boundary conditions, right? So this is true for this component grid, and also for this component grid for this boundary. And for the overlapped regions, we have two interpolation points. So from this graph here, I've shown you the points and its donor points from the other grids, right? So we're going to use the solutions from those 5 donor points to interpolate the values of this one, and vice versa. We're going to use the donor points from here to interpolate the value solutions at this point. Okay, so those last two equations just describe that interpolation. Okay, so anyway, we can rewrite regardless how many single points, how many grids you have, we can write it as the equation into a matrix form, right? So it's a second order derivative with some matrix multiplying my solutions on all the components, on all the grid points, and plus my dissipation, okay? Okay, so to solve this matrix equation using both C2 or UPC2 schemes will lead us to a general updating equations, right? Consisting of the previous 2 solutions and the new solutions, right? So we write it this way, and this Q2, Q1, Q0 will be depending on these matrices here, and they will be different for C2 and the UPC2. And of course, the solution or the stability of this difference equation is related to this eigenvalue problem, right? So this quadratic eigenvalue, so here should be 1, sorry, there's a typo. This quadratic eigenvalue problem, okay? And the scheme is stable provided that all the eigenvalue of this problem is the module or the magnitude of the eigenvalue is less than or equal to 1. right? So we just solve this equation, solve this eigenvalue problem numerically, and we plot the eigenvalues to see why we have a weakly instability for overlapping case. Okay, so the blue dot shows the eigenvalue of the composite grids. The red dot shows the eigenvalue of the single grids. And we also plot this unit circle as a reference to show you that if the eigenvalue is stay inside of this unit circle, it is a stable mode. If it's outside of a unit circle, it's an unstable mode, right? So we can see that for this for both the games, for the single grid case, they stay right on the boundary of this unit circle. So which means both schemes are non-dissipative schemes. So that is what we want for solving this hyperbolic type of equations. We don't want to damp out important features. But because of the presence of interpolation inside of those matrices, okay, so we have interpolation equations inside of those matrices, and it perturbed the eigenvalue of those matrices so that some of them are outside of this unit circle, right? It becomes weakly unstable. And by adding this dissipation, so this one used the C2 scheme, so we add it using the strategy described in our C2 scheme, we are able to stabilize these unstable modes. And also by using the UPC2 scheme strategy, we are also able to stabilize this mode so that it has been dragged inside of this depth inside of this unit circle. So both scheme becomes stable on overlapping grids as well. So similarly, we may find the eigenvalues for the other two methods, PC22 and the NB2 scheme, right? So we know that the PC22 scheme, so ideally it's not a good method for solving hyperbolic equation because the scheme itself is dissipative, so which can be seen from the plots of the eigenvalues without any artificial dissipation. So we can see that the eigenvalues are inside of this unit circle, not right on the boundary. So the scheme is dissipative. So over time, it will be damped out by the scheme. However, the dissipation provided the scheme by the scheme itself is not enough. So we can still observe some unstable modes that hang outside of this unit circle, right? By adding our artificial dissipation as proposed, we can see that we are able to further damp those unstable modes inside of the unit circle to stabilize this scheme. And interesting thing about the numerical beta scheme is that this is an implicit scheme, right? So for implicit scheme, we were told that it's always unconditionally stable. But when we're trying to apply that, it's not stable. So we are wondering why. Well, because this numerical beta scheme, even though it's implicit, this is also a non-dissipative scheme. So you can see that for the single grid case, all my eigenvalues have a magnitude equals 1. So it's not going to be damped out by the scheme itself. So which is perfect for solving this kind of hyperbolic equations. But with a little bit of perturbation caused by the presence of interpolation equations, we can see that we have some modes that is stay outside of this unit circle. Therefore, this makes this scheme is unstable. Right, by adding a little bit artificial dissipation, we are able to stabilize these unstable modes and make our scheme work. And as you can see that the strength of the artificial dissipation we add is not very strong. It's just enough to stabilize the unstable modes, right? So our formulas showed you in earlier page from our analysis have helped us to determine a very good estimate about the strength of artificial dissipation to be added here, so that we are not adding too much of dissipation, but just enough to stabilize the scheme. So this way we can still keep most of this non-dissipative feature of our underlying algorithm, but also stabilize the weakly instability caused by interpolation equations. Okay, so now trying to test whether or not the scheme is working, right? So normally in numerical analysis, or we use this method of manufactured solutions, right? So this is like a method that can be applied anywhere, right? So to test the accuracy of any numerical method is, we don't know how to solve an equation, right? We just manufacture one. So we assume this is our exact solution, and we plug it back into our PDE. Of course, this will not satisfy the PDE. We will have some leftover, but we can keep at leftover as our forcing, right? So we just specify that thing as our forcing and solve it numerically. So the numerical method should match this exact solution. Therefore, we can have some manufacturer solution to compare with and to do mesh refinement study. Okay, so to do that, we just we create a simple overlapping grid. So this one mimics what we did for the 1D simple model problem, right? So we create a unit square, and we have so even though we can discretize this using a single grid, but just to see how this interpolation equation will affect the stability of our scheme, we use a composite overlapping grids that consisting of 2 component grids. Okay, and here we show you the errors of all the components. So the error of W, error of V, and the error of A. So we can see that all the errors are very small. And once we do the careful mesh refinement study, we can see that we carefully examined the convergence of all the WVA for all the boundary conditions we considered. And we can see that for all the cases and for all the numerical methods we considered, they are second order accuracy. It's very consistent. And also, we also like to find some spatial solutions that we know is like the exact solution to test our numerical method, right? So fortunately for circular plates, there are some analytical solution available for some boundary conditions. Okay, so what is the analytical solution for a circular plate? Is that if we're given this initial boundary condition, looks like that. Okay, so here Ji are the nth order basis function and the modified basis function. So J is the basis function, I is the modified basis function of first kind and of order n. If we give this initial condition, we will have an exact solution look like that here. And the value W lambda here depend on the boundary conditions, and they are found by enforcing this exact solution to the boundary conditions, and we end up with some transcendental functions, and the roots of those transcendental functions tells me the values of lambda n. And for the purpose of designing numerical tests, right, we only need to find a couple of roots. That's enough for us to design some exact solution to test. Okay, so these are the plots of the clamped transcendental function and the supported boundary condition. So we can see the lowest, smallest roots of the first 3 orders plotted here, right? By using those 3 different values, we are able to construct this exact solution, and we will be able to compare the exact solution with our numerical solution. Okay, so to do just that, here we show you our computational grids on a circle, right? So obviously this is discretized by our overlapping grid strategy. And okay, so these are the initial condition for the first 3 orders of basis functions, right? Order 0, order 1, and order 2. And after solving that with all the different methods and all the possible boundary conditions we can apply. So for this exact solution, it only supports clamped and the supported boundary conditions. So we just consider those 2 boundary conditions. And again, we see that everything is converging consistently, second order accuracy. And the error is nice and small, okay, for all the W, V, and the acceleration components. So here we only plot the case n equals 2, and it is for the NB2 scheme. And the error behavior is similar for all the other cases. Okay, so as an application, we solve a Kirchhoff-Love plate models. Okay, so we have the perforated plates. So to show you, our method can deal with very complicated geometries like this one, right? So it's very complicated. And we're going to specify some initial displacement, and we can see how this initial displacement will propagate throughout the plates, right? So the formula for this initial displacement is given here, but the plot looks like that. Okay, so I can see for the clamped boundary condition, we can see the displacement looks like that. So because it's being clamped, the wave doesn't travel too much out of the first layer of holes, right? And correspondingly, we have the velocity and the acceleration. So everything looks very nice. And for the free boundary conditions, we can see because it's free to move, it allows to move freely. So the vibration can go through all those holes and can quickly reach out to the boundary. And this is the corresponding velocity and the corresponding acceleration. Okay, And also, as another application, we consider the traveling pulse on a guitar problem. So this is a computational grid for our guitar. And for the inner circle, we have a free. So this is allowed to vibrate freely so that you can have nice music coming out from the guitar. And on the other side, because this side is connected to other parts of your guitar, so this is assumed to be a clamped boundary condition. And we are simulating how this initial traveling wave is going to travel. And when it hits this hole, how it's going to react. Okay, so this is the initial displacement and the velocity we specify for this test problem. And we can see. And for the parameters, first to set of a problem, we set the parameters like a wave, right? So we set the stiffness components to be very small so that it behaves like a wave equation. So our solution captures just like that. So the velocity and the acceleration for that problem. Okay, and the second test, we set the stiffness of the material to be very stiff. So it behaves more like a plate. And our algorithm can capture all the displacement, velocity, and acceleration very nicely. Okay, so to summarize what we did is we developed novel numerical schemes for solving a type of fourth order PDEs in complex domains. And the technique we used to resolve the geometry is called composite overlapping grids. And also because of the existence of interpolation equation on overlapping grids, we have weak numerical instabilities. Therefore, we have proposed some efficient artificial hyper-dissipation to be included into our equation so that it will stabilize the time integration of our schemes. Okay, and what's more, we have used for local Fourier analysis to derive formulas for determining the stable time step and the dissipation coefficient that can be applicable directly in actual computation. So you've seen all the computations, we simply use those formulas in our table. Okay, and we have demonstrated that for finite difference methods together with overlapping grids, we are able to solve plate problems with realistic or complex geometries, right? So there was some finite element people who don't believe finite difference method can solve realistic geometries. So this examples is like a demonstration that we can do that. And because of the mesh we have is structured mesh, so everything should be very more efficient than unstructured meshes that you normally would do to resolve those complex geometries. Okay, and the future directions is that, of course, the model we showed here is a simple linear model. We can solve nonlinear models, and we may develop more solid models, right, depending on what kind of applications we want to use. So we may develop Timoshenko beam model or continuum beam model, Mendeleev-Reissner plate, viscoelastic oyster shell models, elastic shell models, right? Those are a type of models that are often used to model tissues. So if we want to model fluid structure interaction of tissues, so we might want to have that models. Okay, and another direction is, of course, fluid structure interaction. So this is the goal why we started this project, is to have some nice solid structure so that it can be coupled together with our fluid solvers. Okay, so in our recent work, we have developed an added mass partition scheme. It's called AP scheme for solving FSI problems coupling Euler-Bernoulli beam. Right, so the key idea of this AP scheme is by matching the fluid and the solid acceleration, and we derived some new interface boundary conditions, so which is very complicated. But implementing these boundary conditions is much better than implementing the more straightforward boundary conditions, and it stabilizes. So it overcomes issues about added mass instability. So that's beyond the scope of this talk. But this is some good method we developed. And would like to use that for more plates or more solid models. Okay, so here is some movies about our FSI involving beam models, right? So because we have this beam model, that is simple. You can think of it as a 1D plate, right? So still involves fourth order derivatives. And this is a more complicated situation. We have, why it's stopped. Okay, so yeah, so it's more complicated the situation. So we can see we plotted the vorticity here. our AppSkin can handle just that. Once we have more sophisticated solid models, we can do more stuff on FSI. So this is our some preliminary attempt to bring the AppSkin to 3D. So we have a 3D dancing beam to see the fluid structure interaction. And with the development of new solid models, we can do fancier simulations, like we can do hemodynamics applications, like model the computational the blood flow in arteries. So this is the composite overlapping grids we generated for the aortic arch. So you can see looks like that. And also we may do this study the aortic valve. Okay, so this then regulates how your blood flows into your blood. So everything like that. So this valves can be modeled with some kind of shell models. Okay, so some of our collaborators have already started some initial work in this direction. Okay, so why we want to simulate that? Because your natural heart valve can become malfunction, right? So like that, it has to be replaced with some mechanical valves with bileaflets. So in this bileaflets model, our collaborator, Dr. Chi Tang, and has simulated that this is 2D situation. So the plate has been modeled as a rigid body. So there's no internal dynamics here. And this is the 3D version for that. Okay, so the immediate improvement we can do for this model is to replace this rigid solid with our plate model, right? So we can have some more interesting dynamics going on inside of the solids. And also we could consider the tri-leaflet valve. So like you can see here, in reality, we have three valves here regulating the blood flow. Okay, so with that, I'd like to thank you for your attention and any questions?
Great. Thank you very much, Dr. Lee. That's a great talk. Do we have any questions from the audience? Well, I can get started with the question. So I've been wondering about your thoughts on incorporating some weak nonlinearity into the fourth order PDEs. So what do you think would be the largest challenge of bringing in some weakly nonlinearity into these hyperbolic PDEs? For example, things like the thin film equation kind of.
Yeah, I think the largest, I mean, we can always use Newton's method. It will definitely work, right? So, but together with our discretization techniques, so we have our matrix and solve it using Newton iteration. I mean, the challenge is how to make it faster, right? So we don't want to do maybe fully implicit. Maybe we can. I mean, the efficiency depends on how much explicitly we can build into our algorithm, right? So the more explicit, the more efficient it will be. So I think that would be an interesting research direction to look at. But if you simply want it to work, we can use Newton's method, so it will work. And we have our studies on, I've studied tear film, so we have Newton's method for solving that, and it works.
Great, thank you.
Andy, can I ask a question?
Yeah, please go ahead.
Yeah, I actually have a few of them. So one, so this dissipation coefficient, is that something you determine for every cell or every grid point, or is that just one computation for the whole domain?
Yeah, right now we are using for the one computation, and we're using the minimum cell length to determine that. Okay, so ideally, if you have a very different mesh here, if you have a very different mesh, then you might want to have that determined according to the cell length of different cells, right? Yeah. But because we're using composite overlapping grids, our grids, both component grids, we're trying to build component grids that are of similar size. Therefore, by using a single mesh size to determine the coefficient is sufficient for us.
I mean, but presumably it doesn't depend on the cell size, but the properties of the solution at that point, right? So you could have some region where there's a lot of action happening. Again, I'm not a PD I'm not a PD person, so I don't know. But maybe you have a lot of changes in one area you may want to have.
Well, yeah, those things are, we can always do adaptive mesh refinement over there to resolve that. But those kind of question is not related to the weak instability caused by the interpolation equation. Those are some other, like you're trying to capture a shot, something like that. You have to do that. But those are different type of questions.
Okay. And so what's the cost? So you're saying that to determine that coefficient, you just look at the cell size, and so there's no cost associated with estimating that coefficient. Is that what you're saying?
No. So we have this formula
okay.
Analytically. So the only cost is to evaluate this formula at c equals pi and or negative pi.
And so you're not actually solving that. Is that an ODE? Are you actually solving that ODE, or is it just something?
We solve it analytically. We derive the bound, analytical bound. So we have the formulas here. Once we have an estimate for this Q hat, so this Q hat is like the corresponding to the modes of the worst case scenario. So we have an estimate for that. This will only involve some function evaluation. So very complicated function evaluation. So and this is done only once. So it's not efficiently speaking, it's not it's fine. I mean, all our simulations here you can see is done on my laptop.
Sure.
Minutes.
Yeah. So hyperbolic, it's I guess you can do it on a laptop. That's not
okay. Yeah.
Well, if I can ask one more question, which is so you mentioned finite difference versus finite element. I mean, I don't want to get into the full discussion, but how are you exploiting structured grids here? Like, how is that computationally advantageous here?
Well, the computational
simulations.
Well, the most obvious computational advantage is if you're using a structured grid, right? So normally, if you have like you're trying to discretize second derivative, you have a tri-diagonal mesh, a tri-diagonal matrix, and if it's structured, the coefficients is the same on the diagonals. They are not different, right?
I see. But you're not solving linear systems. It's just a matrix vector product, right? So is there really a lot of advantage of a finite difference?
Yeah, I mean, if the size of these numbers are the same, so which means the structure or the condition number of your matrix would be nice. But if you have unstructured meshes, right? So you might have some parts that have a very small number.
Right.
You might have some other parts, you might have a very large number. So the condition number of your matrix may be bad, and it can be very costly for solving those.
But you don't have a solve. I mean, is the idea that when you put it inside a nonlinear solver, things break down? Because right now you have an explicit scheme, so you don't have any linear systems.
We have. I mean, for the numerical beta scheme, it's implicit scheme.
Oh, I see. Okay.
We are inverting the matrices here.
I see.
Numerical beta scheme.
I see. Sorry, I missed that.
Yeah, here we're inverting this matrix here, right? For all the other scheme, it's explicit. And also, let's go back to the Hangji's question. If we want to do nonlinear equations, we have to solve, right? And the nicer the structure of these matrices are, the better we are off, right, in terms of performance.
Okay. Yeah. Thanks. That's all.
Okay, that's great. Do we have any other questions from the audience? Okay, great. Let's thank our speaker again. Thank you very much for giving this nice talk here.
Okay, thank you for coming. Thanks for the invitation.
Thank you. I'll see everybody next week. Thank you.
Okay, bye.
Bye.